Okay, well, let's move on. The next topic we're going to talk about is discussed in Chapter 9, and it's simple optimization theory, Chapter 9. And before I talk about simple optimization theory, let me discuss the concept of higher order derivatives, second derivatives, third derivatives, fourth derivatives. As it turns out that the second derivative plays a crucial role. The sign of the second derivative plays a crucial role in distinguishing a minimum from a maximum. So that's why I want to go over this first. Let's take a simple quadratic function first. We're dealing with a simple case where y is a function of x. And suppose we have a quadratic function of this form, a plus bx plus cx squared, where a, b, and c are parameters. They could be positive or negative. The only thing we want to assume here, if this is a quadratic, let's just assume that c does not equal 0. Otherwise, it would just be a linear equation. So let's just assume for right now that c does not equal 0. Okay. Then what is the first derivative of this function, f prime of x? Okay, it's just b plus 2cx. Now, notice this first derivative function is a function of x. The first derivative itself is a function of x. It depends on the value of x. If I give you the value of x and you know the value of b and c, you just plug into this equation. Out pops the first derivative. And geometrically, what is the interpretation of the first derivative at a given value of x? Yeah, it's just the slope of the function, f of x, at that point, x. Okay, so it gives you the point slope. Suppose, since the first derivative function is clearly a function of x, we could differentiate it. So if we differentiate the first derivative, we get the second derivative. And let f double prime of x denote the second derivative. It's the derivative of the derivative. So what is the second derivative here? If you just differentiate this with respect to x, you get 2c. Okay. The sign of the second derivative depends on the sign of c. If c is positive, the second derivative would always be positive. If c is negative, the second derivative would always be negative. Okay. Let's suppose c is positive. Now, how would you describe the meaning of that in words? Or what does that mean if the second derivative is positive? Recall that the derivative is the point slope. It's the rate of change of y with respect to x. So then what is the second derivative in words? Yes, exactly. If the first derivative is the point slope, then the second derivative is the rate of change of the point slope at a given point. And it tells you whether the slope is getting bigger or smaller as x gets bigger. Okay. So a positive second derivative then would mean what? well, let's be careful. We don't know what the sign of the first derivative is. Could be positive or negative. But the fact that the second derivative is positive means what, Ben? Okay, it means that the first derivative, let's take an increase in x. If x gets bigger, what happens if x gets bigger? If the c is greater than 0, the second derivative is positive. Okay. Just describe it in words, what you said before. Suppose x gets larger. What is happening to the first derivative? Yes. Yes. Yes, the slope is getting, okay, be careful. What it means is the slope is getting larger. Now that could mean one of two things. If the slope is positive, it means it's becoming more positive, as you said, steeper. But what if the slope were negative? No. Actually, algebraically, it means less negative. Bigger means less negative. Because this is really telling you algebraically what's happening. This is getting a little abstract. Let's look at a specific example. Okay. Let's take this example right here. Okay, 100x minus x squared. What's the first derivative? Heather? 100? Remember, I'm hard of hearing.
Minus 2x.
Thank you. Minus 2x. Okay, that's the first derivative. And this equation will give us the rate of change of this function with respect to x at any given point. If you give me a value of x, this first derivative geometrically is just the point slope of the function at any point of x. What is f? What's the second derivative? F double prime of x. Negative 2. In this case, the second derivative is always a negative. So what this means is as x gets larger, the first derivative gets smaller. Now what that would mean is if the first derivative were positive, it would become less positive as x gets bigger. If the first derivative were negative, it would mean it becomes more negative. Okay. Yeah, no, that's okay. All right, so, but let's take this a step further. Suppose we want to sketch this function. Now, I'm very big on sketching. Let the dependent variable be y. So on the vertical axis, you have y or f of x. Okay, let's just suppose we have y equals f of x. What would the graph look like? We know it's a quadratic equation. Its graph is a parabola. The coefficient on x squared is negative. So what general type shape is this function going to have? Okay, it's going to be upside down u, because the coefficient on x squared is negative. We know parabolas are either u-shaped or upside down u. Because the coefficient on x squared is negative, it's going to be upside down u. And what is the vertical intercept? 0. Notice if x is 0, y is 0. So it comes out of the origin. It's going to be an upside down u. So it's going to look like this. Okay. Now, an interesting question would be, where does this reach its top? This looks like a hill. At what value of x do you reach the top of that hill? How would we find that? Right, set the first derivative equal to 0. Because what's the geometrical interpretation of the first derivative? Point slope. And at the top of the hill, what's the point slope going to be at the very top? 0. Okay. So notice if you get to the very top of this hill, let me make sure this is horizontal. You get to the very top, point slope is going to be 0. So at this point right here, and let's call this value x sub 0. We don't know what it is yet. F prime of x sub 0 equals 0. Okay. How would we find x sub 0? By the way, in mathematical terminology, x sub 0 is called the critical value of x. The critical value of x. The value of x where the first derivative is 0. It's called the critical value of x. Okay. Where f prime of x is 0. How would we find x sub 0 in this case? Jonathan, I can tell you want to answer.
How would we find what?
How would we find the critical value of x?
Just that f prime of x equals 0.
Exactly. We know at the critical value of x, f prime of x has to be 0 by definition. So all you do is go back to this equation right here, set that first derivative equal to 0 and solve for x. And this would be easy. We give 100 minus 2x equals 0, so add 2x to both sides. We get 100 equals 2x. Divide both sides by 2, and you get 50 equals x sub 0. Okay. So our critical value of x is 50. Okay, so we can put this value in. And this value of y that corresponds to the critical value of x, f of x sub 0, more generally is just called the stationary value of y. Of, in this case, the function, or y. We'll just call it y, since y is equal to f of x. That's the stationary value of y. Okay. And we'll just call that y sub 0, or f of 50. And what is f of 50? Now notice, in order to get this, you have to go back to the original function. So what is f of 50 in this case? Yeah, just go back to this equation right here and substitute 50 for x. So you get 100 times 50 minus 50 squared. 100 times 50 is 5,000. 50 squared is 2,500. So it is a 5,000 minus 2,500 equals 2,500. Okay, so this stationary value of y is 2,500. And in this particular case, this 2,500 is also, what is it in this case? It's pretty obvious from looking at the graph. Yeah, it's also the maximum value of the function. Okay. In some cases, the stationary value of y will turn out to be not a maximum but a minimum. Or it could be corresponding to an inflection point, which would be neither a maximum nor a minimum. Okay. But in this case, it turns out to be a maximum. Okay. So we have this point slope right here is equal to 0. Now, we've already figured out in this function, the second derivative is always negative. Notice in this case, the second derivative is a constant, meaning it always, in this case, is always negative. So, can you see that from the diagram? Ben, if this second derivative is negative at this value of x, then what happens to the point slope as x gets bigger? Yeah, it gets smaller. So originally it was 0. But if x increases by just a little bit, then the first derivative is going to become negative. If it's getting smaller, it's going to go from 0 to negative. And you can see that from the graph. If you just slightly increase the value of x, just by a small amount, then you can see what's happening. The slope is going to then become negative. Okay. If you decrease the value of x, though, the slope gets bigger. The slope and the value of x move in the opposite direction. So if you decrease x, the slope is actually going to get bigger. And you can also see that in the graph. If you go slightly to the left of 50, you can see then slightly to the left the slope is going to be positive. So the rate of change of the first derivative is positive, 0, negative. That's a negative rate of change. Okay. So a negative second derivative in conjunction with a first derivative that's 0 guarantees that you have what at x of 0? A maximum. Okay. So a 0 first derivative in conjunction with a negative second derivative ensures that you have a maximum. And this is really the test for a maximum. Find out where the first derivative is 0, then check the second derivative. Should the second derivative be negative, then that guarantees that you have a maximum at that critical value of x. Yes?
Just to restate, so a constant negative second derivative means that the slope of the tangent line is going to continuously decrease?
It means, yes, the x and the first derivative, or the point slope, x and the point slope, move in the opposite direction. As x gets bigger, the point slope gets smaller.
So if it's a constant positive, that means that the
Yes.
slope of the tangent line is constantly decreasing?
Yes, let's take that case. In this case, we had, now let me just rephrase what you said. Actually, in this particular case, the second derivative was constant. But that's not the important thing. The important thing is whether the second derivative is positive or negative. So really the important thing is, for optimization, the sign of the second derivative at the point where the first derivative is 0. If it's negative, that guarantees a maximum. You know, wouldn't have to necessarily, the second derivative wouldn't have to necessarily be constant. It's just the fact that it's negative that's important.
But wouldn't there be, like, if you had a function where it had one maximum but another?
Yeah, you could have that. This test is really a local test for a maximum in a small region around the critical value of x. Yes, but you're raising some good points, yeah, that we'll talk about later. Yeah.
Just remember that the second derivative is greater than 0 if it's concave up, and the second derivative is less than 0 if it's concave down.
Yes.
Pretty much get that shape that,
Exactly. That's exactly. The second derivative being negative means it's concave. Sometimes this is called concave down. Or more generally, in economics, this is just called concave. But if it were a positive second derivative, then you'd have to flip this around. It'd have the opposite shape. And then that would guarantee a minimum.